Good evening, ladies and gentlemen, distinguished scholars, curious minds, and those of you who have wandered in hoping for a magic lantern show and found instead a Scotsman with a penchant for invisible forces. My name is James Clerk Maxwell, Professor of Experimental Physics at the Cavendish Laboratory in Cambridge, though I confess the title still feels a trifle grand for a lad raised among the heather and sheep of Galloway. Tonight, I stand before you not as a lecturer in the usual sense, but as something of a travelling salesman, yes, a salesman of ideas. For I have lately completed a rather substantial work, a labour of love that has occupied many a late night and early morning, my 2-volume treatise on electricity and magnetism. It is my earnest hope that you will forgive the immodesty of the occasion, for I come bearing good news. The invisible powers that surround us, those mysterious agencies we call electricity and magnetism, are no longer strangers. They have been introduced to one another, shaken hands, and discovered they are, in truth, two aspects of the very same phenomenon. And light, yes, the very light by which you now see my rather earnest face, is their swift-footed cousin, racing through the ether at precisely the same speed. But I get ahead of myself. Allow me first to tell you a little of how I came to this curious pursuit. When I was a boy of 8 or 9, growing up at Glenlair in Kirkcudbrightshire, I was forever asking my father, what is the go of it? Meaning, what makes things move? What makes the wheels turn? What makes the thunder roll? My father, patient man that he was, would answer as best he could, though I suspect he sometimes wished I had taken more interest in sheep shearing than in the hidden machinery of the universe. That same question has never left me. I have chased it through the corridors of Edinburgh University, through the cloisters of Trinity College, Cambridge, and into the quiet rooms where I could sit with Faraday's experimental researches and ponder the beautiful lines of force he so lovingly described. Now, after many years, I have attempted to gather those scattered discoveries, those of Coulomb and Ampere, of Ørsted and Faraday, and of many others, into a single coherent picture. The result is my treatise, published just last year by the Clarendon Press. 2 stout volumes, I fear, not exactly light reading for the fireside, but I promise you they contain no unnecessary mathematics, only what is strictly required to make the invisible visible to the mind's eye. Volume the first deals with electrostatics and magnetostatics, the forces between stationary charges and steady magnets, the potential, the capacity of conductors, the distribution of electricity upon surfaces, and the curious behavior of dielectrics. Volume the second carries us into the realm of motion, currents, induction, electromagnetic waves, and the grand unification I have ventured to propose. Tonight, I shall not attempt to read the treatise to you. That would be a cruel punishment for both speaker and audience. Instead, I propose to take you on a guided tour of its principal ideas, describing everything as plainly and vividly as words alone can manage, as if we were gathered round a fire on a winter's evening in Edinburgh. We shall begin with the foundations laid by earlier workers, those sturdy stones upon which the whole edifice rests. We shall then examine the bridges I have attempted to build between electricity and magnetism, the new concept of the field that makes those bridges possible, and finally the astonishing conclusion that light itself is an electromagnetic disturbance. Along the way, I shall endeavour to keep the language plain, the descriptions clear, and, if the good Lord grants me the grace, the occasional jest. For I have long believed that truth is best served with a little wit, lest she grow too solemn and frighten away her admirers. So, if you will indulge me, let us embark. Imagine, if you will, that we stand at the edge of a vast and invisible ocean, an ocean of force and energy that laps at every wire, every compass needle, every sunbeam. Most of us have lived our lives quite unaware of its tides. Tonight, I hope to persuade you that this ocean is real, that its laws are beautiful, and that we have only just begun to sail upon it. And should any of you leave this hall tonight thinking, I must have that treatise, I shall consider the evening a complete success, though I warn you the bookseller may charge you a pretty penny for the privilege. Now, let us begin at the beginning, with the amber of the ancients, the lodestone of the mariners, and the first sparks of understanding that set us on this marvellous journey. Let us now step back, as it were, to the nursery of our science, where the first discoveries were made, often by accident, sometimes by brilliant insight, and always with a good deal of astonishment. We begin with electricity in its simplest, most ancient form, the amber effect. The Greeks knew it 2,000 years ago. They called the substance electron, amber, and noticed that when rubbed with fur or wool, it would attract feathers, bits of straw, even small pieces of metal. Thales of Miletus remarked upon it, though he thought the amber had acquired a soul. We smile at the notion now, but how much closer were they to the truth than they knew? For what is a charge but a kind of restless spirit that seeks its opposite? Fast forward to the 18th century, and we come to Benjamin Franklin, printer, statesman, and one of the boldest experimenters who ever flew a kite in a thunderstorm. Franklin showed that the spark from your finger after shuffling across a carpet is the same agency as the lightning that splits the sky. He proved it with his famous kite experiment in 1752. A key tied to the string drew sparks from the clouds themselves. Electricity, he declared, is one fluid, present everywhere in different quantities. When in excess in one place and deficient in another, it rushes to restore the balance. Positive and negative, he called them, though I confess I still prefer his older terms of vitreous and resinous for their poetic ring. Then came Charles-Augustin de Coulomb, a French engineer with a delicate torsion balance of his own invention. In the 1780s, he measured the force between charged bodies with exquisite precision and found it follows the same law as gravity. The force is inversely as the square of the distance and directly proportional to the product of the charges. A simple law, yet it governs everything from the behavior of dust motes to the structure of the world around us. So much for stationary electricity. But electricity that sits still is only half the story. The other half begins with a compass needle and a wire. In 1820, Hans Christian Ørsted, a Danish philosopher and physicist, was demonstrating to his students the heating effect of a current in a wire. By chance, or by providence, the wire lay near a magnetic compass. When he closed the circuit, the needle swung, not toward the wire, as one might expect, but perpendicular to it. Electricity in motion produces magnetism. The age of electromagnetism had dawned. Within weeks, André-Marie Ampère in Paris had taken up the discovery and turned it into a science. He showed that two parallel wires carrying currents attract or repel one another, depending on whether the currents flow in the same or opposite directions. He invented the word electrodynamics and gave us the law that now bears his name. The magnetic force exerted by a current element upon another is proportional to the product of the currents and inversely to the square of the distance, with a curious angular dependence that makes circles of force rather than straight lines. And then there is Michael Faraday, my great teacher, though we never met in the flesh. Faraday was a bookbinder's apprentice who taught himself science from the lectures of Humphrey Davy, then became Davy's assistant and eventually surpassed his master. He had no formal mathematics, yet his intuition was unmatched. In 1831, Faraday discovered electromagnetic induction. If you move a magnet near a coil of wire, or move the coil near the magnet, a current flows in the wire, even though no battery is present. change is the key. A steady magnetic field does nothing, but a changing one induces an electromotive force. Faraday also found that a current in one circuit can induce a current in a neighboring circuit, even with no direct connection, the birth of the transformer. He spoke always of lines of force. He pictured them as real, elastic threads stretching through space, crowding together where the force is strong, spreading out where it is weak. If you were to sprinkle iron filings on paper above a bar magnet, you would see those lines traced out in graceful curves, streaming from one pole, arching through space, and returning to the other, forming closed loops that never quite end. These, then, are the principal foundations upon which my treatise is built. The electrostatic force of Coulomb, the magnetic effects of steady currents discovered by Ørsted and quantified by Ampere, the induction of currents by changing magnetic fields revealed by Faraday. Yet notice how disjointed they remained. Electrostatics dealt with charges at rest. Magnetostatics dealt with magnets or steady currents. Induction required motion or change. No one had shown that electricity and magnetism were truly two sides of the same coin, nor that they could exist without matter at all, propagating freely through empty space. That gap, that missing link, is what I have tried to supply. In the next part of our journey, I shall introduce you to the concept that binds them together, the electromagnetic field. Not a substance, not a fluid, but a state of space itself, a condition in which forces are prepared to act the moment a charge or current appears. It is a bold idea, perhaps, but one that has already begun to bear fruit. So, with these foundations firmly in mind, let us now cross the bridge I have attempted to build between the world of stationary charges and the world of moving ones. The journey becomes rather more adventurous from here. And now, my friends, we arrive at the very core of the matter, the bridge I have endeavoured to construct between the realms of electricity at rest and electricity in motion, between the static and the dynamic, between the seen sparks and the unseen waves. To do this, I have found it necessary to introduce a new way of thinking about these forces, not as actions at a distance between particles, but as conditions or states of the space itself. I call these states fields. An electric field is the condition of space that would exert a force upon a charge placed there. A magnetic field is the condition that would exert a force upon a moving charge or a magnet. These fields are not mere mathematical conveniences. They are as real as the ether through which they propagate, and they carry energy, momentum, and the very possibility of distant action without direct contact. Let us consider first the two great laws that describe how these fields begin and end, or, in the case of magnetism, how they never truly begin or end at all. The first is what we now term Gauss's law for electricity. Imagine a closed surface, say an imaginary balloon, surrounding some electric charges. The total amount of electric field passing outward through that surface is exactly equal to the charge enclosed divided by a constant of nature. In plain words, electric field lines begin on positive charges and end on negative charges. They do not appear from nowhere or vanish into nothing. The more charge inside your imaginary balloon, the more field lines burst forth. For magnetism proper, the corresponding law is even more austere. The net amount of magnetic field passing through any closed surface is always zero. There are no isolated magnetic poles, no magnetic monopoles, as some might fancifully call them. Magnetic field lines are always closed loops. They neither begin nor end. This is why a magnet cut in half does not yield a lone north or south pole. Each half simply becomes a smaller magnet with both poles intact. These two laws tell us about the sources of the fields, but the true magic, the unification, lies in the laws that describe how the fields change and influence one another. Third comes Faraday's law of induction, which I have expressed in precise mathematical form. A changing magnetic field through a loop induces an electromotive force around that loop, tending to drive a current. The induced electromotive force is equal to the negative rate of change of the magnetic flux through the surface bounded by the loop. This is why moving a magnet near a coil causes current to flow, or why a varying current in one coil can induce current in another. Change in the magnetic realm begets force in the electric realm. And here is the crown of the whole theory, the addition I ventured to make to Ampere's circuital law. Ampere had shown that a steady current produces a magnetic field curling around it. But what of changing electric fields? Consider a capacitor being charged. Current flows in the wires, but between the plates there is no conduction current, only a growing electric field as charges accumulate. Yet, if we are to have consistency, the magnetic field must continue unbroken around the circuit. To resolve this, I introduced what I called the displacement current. In a dielectric, or even in empty space, a changing electric field acts as if it were a continuation of the current. The total current, the conduction current plus this displacement current, is what produces the magnetic field. The curl of the magnetic field around any loop is proportional to the total current threading through it. This simple addition, displacement current, completes the symmetry. Now we have changing magnetic field induces electric field, Faraday. Changing electric field induces magnetic field, my addition to Ampere. A changing electric field begets a changing magnetic field, which in turn begets a changing electric field, and so on. These mutually sustaining fields can propagate through space as a wave, even in the utter absence of matter. From the equations, one can derive a wave equation for these fields. The speed of propagation turns out to be precisely the ratio of the electrostatic and electromagnetic units of charge, measured independently in the laboratory, which equals the known speed of light in vacuum. Light, therefore, is an electromagnetic disturbance, a transverse wave of electric and magnetic fields oscillating perpendicular to each other and to the direction of travel, racing through the luminiferous ether at 300 million meters per second. In my treatise, volume the first lays the groundwork with electrostatics and magnetostatics, potentials, capacities, dielectrics, and the mathematical apparatus needed to describe them. Volume the second advances to currents, induction, and finally, in Part 4, the general dynamical equations of the electromagnetic field. I do not claim these equations are the final word. Science is ever advancing, but they encompass all known phenomena of electricity and magnetism in a unified, elegant framework. They predict not only the propagation of light, but also the possibility of other electromagnetic waves at different frequencies, though I leave it to future experimenters to explore those realms. To illustrate the power of displacement, current in words alone, in a charging capacitor, the displacement current between the plates ensures the magnetic field encircles the entire circuit as if the current flowed straight through the gap. Without it, Ampere's law would fail, and the continuity of nature would be broken. With it, the theory sings in harmony. Thus, ladies and gentlemen, electricity, magnetism, and light stand revealed as one grand phenomenon. The treatise is my attempt to set this truth down in full mathematical rigor, yet always with an eye to Faraday's intuitive genius and the beauty of nature's design. We have crossed the bridge. On the far shore lie applications to telegraphs, dynamos, and perhaps one day though I speak with caution, means of signaling without wires across the ether. But that is for the future. For now, let us marvel at the unity we have glimpsed. In the next part, we shall explore some broader curiosities and implications of this theory, and perhaps indulge in a few of my own lesser-known pursuits. We have now traversed the main edifice of the treatise, ladies and gentlemen, and glimpsed the grand unification of electricity, magnetism, and light. Yet the story does not end at the final page. The ideas I have set forth send ripples outward, touching other branches of knowledge, inspiring new experiments, and even provoking a few philosophical musings over a cup of tea. First, allow me to confess that electricity and magnetism are not my only passions. I have long been fascinated by colour, the very hues that paint the world around us. In 1861, working with Thomas Sutton, I produced what is believed to be the first true colour photograph, a tartan ribbon, captured by taking 3 separate exposures through red, green, and blue filters, then recombining them. This method, based on the 3 colour theory I developed, shows that any colour can be matched by mixing appropriate amounts of 3 primaries. And now, with light understood as an electromagnetic wave, we see why. The different frequencies of these waves correspond to the different sensations of red, green, and blue in the eye. Nature's palette is written in the oscillations of the field itself. Turning to another curiosity, the kinetic theory of gases. I have attempted to explain the properties of gases, pressure, temperature, diffusion, by supposing that molecules are in ceaseless motion, colliding like billiard balls in 3 dimensions. The average kinetic energy of these molecules determines the temperature. The distribution of their speeds follows what we now call the Maxwell-Boltzmann law. This statistical approach, though probabilistic, yields remarkably accurate predictions for the behavior of gases. What ties this to electromagnetism? Light, as an electromagnetic wave, interacts with matter, absorbed, reflected, scattered, precisely because molecules respond to the oscillating fields. The color of a gas, the blue of the sky from scattering of shorter wavelengths, the red of sunsets, all follow from the electromagnetic nature of light-meeting molecular scatterers. And then there is the little thought experiment that has amused and perplexed many, Maxwell's demon. Imagine a tiny, intelligent being who guards a small door between 2 chambers filled with gas at the same temperature. The demon allows fast molecules to pass one way and slow ones the other, seemingly separating hot from cold without expending work, defying the second law of thermodynamics. Of course, the demon must expend energy to observe and decide, and when one accounts for the information it processes, the entropy increase appears elsewhere. It is a mischievous imp, but one that forces us to think deeply about the foundations of heat and order. The practical fruits of electromagnetic theory are already ripening. The telegraph, improved by induction coils and better understanding of currents, spans continents. Dynamo machines based on Faraday's induction generate electricity more efficiently. Electric lighting, arc lamps, and the emerging incandescent varieties promise to banish the darkness of our streets and homes. And who knows? The waves I have predicted, travelling at the speed of light, might one day carry messages across oceans without wires, though such a thing would require apparatus far beyond our present means. Philosophically, I find great comfort in this unity. The same laws that govern the spark from a cat's fur govern the aurora borealis and the rainbow. The mathematics is elegant, the phenomena beautiful. As a man of faith, I see in these discoveries the handiwork of a creator who delights in order and harmony. The universe is not a chaos of separate forces, but a symphony with electricity, magnetism, and light as different instruments playing the same score. Yet science is humble. My equations describe what we observe. They do not explain why nature should be so constituted. That deeper question remains for philosophers, theologians, and perhaps future generations. In the treatise, I have tried to present the facts as they stand, with the mathematics as a faithful servant rather than a master. I have drawn heavily on Faraday's intuition, Ampere's rigour, and the experiments of many others. If the work endures, it will be because it points toward truth, not because it is flawless. We stand then at the threshold of a new era in natural philosophy. The invisible has been made visible to reason. The disconnected has been united. May future workers build upon these foundations, correct any errors I have made, and reveal yet greater beauties. In our final section, we shall draw the evening to a close with some reflections and an invitation to join in the great adventure of science. And so, dear friends, we reach the close of our evening's journey through the invisible realms. We have walked together from the ancient wonder of rubbed amber to the modern marvel of induction, from the steady hum of a compass needle to the swift flight of light itself as an electromagnetic wave. We have seen how separate discoveries, each brilliant in its day, have been gathered into a single harmonious picture. The electromagnetic field, whose laws I have attempted to set down in my treatise on electricity and magnetism. If I have succeeded in conveying even a fraction of the beauty and unity that lie behind these phenomena, then the evening has not been wasted. For the greatest reward of science is not merely to predict or to harness, but to behold, to stand in astonishment before the elegance of nature's design, and to feel, however faintly, that we have glimpsed something of the mind that fashioned it. Let me leave you with 3 simple truths that I hope will linger long after the gas lamps are dimmed. First, electricity and magnetism are not 2 separate forces. They are one. The spark that jumps from your finger and the pull that turns the compass needle are brothers, born of the same invisible field. Second, change is the great engine. A steady field does little. It is the changing electric field that begets the magnetic, and the changing magnetic that begets the electric. In that endless dance, light itself is born and races across the universe. Third, we have only begun. The equations I have written describe what we know today. Tomorrow's experimenters, perhaps some of you in this very hall, will test them, refine them, extend them. They may discover new waves, new interactions, new applications that will astonish us all. The ether may yet reveal secrets we cannot now imagine. I commend to you, then, the 2 volumes of the treatise. They are not light bedside reading, I grant you, but they are written with care, with respect for the facts, and with a sincere desire to make the invisible intelligible. If you find them heavy-going, take heart. Faraday himself had no mathematics, yet he saw farther than most. The ideas matter more than the symbols. Before we part, allow me to entertain a few questions that have often arisen in such gatherings. One gentleman might ask, Professor Maxwell, how will this affect daily life? I answer, already we see telegraphs carrying words across oceans in minutes. Dynamo machines promise cheap and abundant electric power. Lighting without flame may one day brighten our homes and streets. And if my prediction of electromagnetic waves proves true, we may yet converse across distances without wires, as easily as we now speak face to face. Another might inquire, is this the final theory? No theory is final. Each is a map, drawn as accurately as our instruments allow. The map improves with every new survey. I trust the map I have drawn will serve for many a journey, but I should be disappointed if future travellers did not find better paths. And finally, the question I am asked most often, Do you really believe light is an electromagnetic wave? I do. The mathematics insists upon it, the speed matches precisely, and the phenomena fit like pieces of a puzzle long scattered. Yet belief in science is provisional. It awaits the verdict of experiment. I await that verdict with confidence and with curiosity. My friends, thank you for your kind attention, for your patience with my Scottish accent, and for the honour of sharing these ideas with you. Science is not the private preserve of professors, it is the common inheritance of all who wonder at the world. Go forth, then, and wonder. Rub a bit of amber, move a magnet near a coil, watch the aurora flicker, or simply gaze at a rainbow, and remember that behind each of these humble marvels lies the same grand symphony of field and wave. May your minds be as charged as a Leyden jar, your curiosity as persistent as a galvanometer needle, and your hearts as steady as the ether itself. Good night, and God bless you all.